Good afternoon. My name is George Lewis. I'm a senior manager for software development for Amazon S3. And I'm joined by Andrew Krudge, the general manager for Amazon FSx for Lustre. And today we're going to talk about high performance storage for AI, ML, analytics, and HPC workloads. What we're going to attempt today is we're going to discuss both file and object-based high performance storage. We're going to do a little bit of compare and contrast right there and try to help you make a decision on what is the right high performance storage solution for your workloads. Let's start off with talking about what do we mean by a high performance workload. Whether you're training large artificial intelligence models, whether you're doing high frequency trading algorithms and risk analysis, or generating on-the-spot media content. At its core, a high-performance workload is any process or application that requires rapid access to extremely large data sets. Generally, this access needs to be in parallel, and generally it needs to have low latency. These workloads are growing, fueled by larger and larger data sets. This is obviously an exponential growth over time right there, and this is just not by accident. This is being driven by the latest advents in compute technology, particularly purpose-built GPUs and AI chipsets that allow us to have larger and larger data sets that we can comb through and find strong inferences. Our algorithms and deep learning techniques have, particularly over the last couple of years, progressed to the point where it can utilize highly enriched data sets to pull out the inferences that before were just kind of lost in the mud. The key to these workloads and large data sets is that they push your standard storage solutions to their absolute limit and require us to continuously innovate to provide the right type of performance. I'm now going to hand it over to Andrew here, who's going to talk about how these workloads use storage.
Cool. Thanks, George. So as George mentioned earlier in the presentation, the focus of this session is really going to be around our file and our object solutions. And the reason for this is when we look at high-performance workloads, typically these are workloads where you have tens, hundreds, thousands of simultaneous compute or GPU instances that are performing a common task. And so typically these solutions end up using shared storage, like network-attached file storage or object storage, as opposed to local storage, like local NVMe drives or EBS volumes. Typically when we look at high-performance workloads, there are a few common ways in which storage is used. The first is, at its core, many of these workloads rely on processing some data that you have stored. You start with a certain data set, you want to analyze it, summarize it, build a model based on it. Step one is take that data that you have and load it into your compute and GPU instances. Sometimes what this means is copying the data into local storage on each of your instances. Most commonly, actually, what customers end up doing is streaming the data directly from these shared storage solutions into their instances as their workloads are running. The second use case we see is something called checkpointing, which checkpointing at a high level, what it means is you periodically, as you're running your workload, maybe every few minutes, you take a state of the model that's running and you write that model off to storage. And the reason you would do this is so that, let's say you have a compute cluster of hundreds or thousands of instances. If there happens to be a failure of one of those instances, with a checkpoint, having a checkpoint allows you to then, once you've taken that instance, replaced it with a new one, you can resume your workload from the last checkpoint that you'd written. Without a checkpoint, oftentimes, depending on the application, you need to actually start the workload from scratch. So as you can imagine, especially as you have larger and larger compute clusters with more nodes, the need for something like checkpointing also increases over time. And so for checkpointing, very often applications are actually paused on doing their actual work while these checkpoints are being written out. And so writing checkpoints as quickly as possible, and then also being able to read these checkpoints back as quickly as possible in the event that you have a compute instance failure becomes super important to make sure you can quickly resume your workload. Lastly, at the end of most of these jobs, you have some sort of a result data set, whether it's an output, report, a model of some sort. This gets written off to some storage solution as well. So typically for high-performance workloads, and the focus of this session is really going to be around the first two use cases, data loading and checkpointing. simply because these are the use cases that have the most stringent performance requirements for storage. So speaking of performance, why is it that storage performance matters? Well, one of the things we commonly hear from customers is they love that with AWS, they can spin up really large compute clusters of many, many instances, run a workload at a much faster velocity than they otherwise could elsewhere, and then they could spin them down once they're done and not need to pay for those resources. Ideally, the more compute instances you add to your cluster, the faster your workload runs. And in an ideal world, this scales pretty linearly with the size of your cluster. Now, a challenge we sometimes see is for customers who are using a storage solution that is not optimized for performance or that doesn't deliver the performance that's needed for the given workload, sometimes that storage solution can end up becoming a bottleneck. And ultimately, what that means is it limits your ability to scale your workload beyond a certain level of performance. This means that you're either not able to get time to results as quickly as you want, or it may mean that you have CPU or GPU resources that, frankly, are underutilized. And George and I are both storage folks. We think about storage all the time. But the reality is, for these workloads, compute is the most valuable resource. Typically, 90 to 95% of the spend on these high-performance workloads is not on the storage. It's on the compute instances themselves. So when we think about storage's role in these workloads, very often really what we're optimizing for on the storage side is making sure storage is fast enough so it's not a consideration, so your GPUs and your CPUs are fully fed, and you're really bottlenecked by the limit of the compute resources that you've provisioned. When we talk to customers about choosing storage solutions for high-performance workloads, at a high level, there are really three key considerations that we see customers make. And we're going to dive a little bit more into each of these throughout the course of the presentation. The first is protocol. How do you access your data? A lot of customers we speak to have existing tools, applications, environments that are written to access data a certain way. And we want to make sure it's easy for customers to be able to continue accessing their data in that same way with new workloads that they build. The second is throughput. Throughput most commonly is a measure of how many bytes per second you can read or write to storage. At the scale of high-performance workloads, typically this is closer to gigabytes or terabytes per second. That's one unit of throughput. The other one, and this is most common for workloads that deal with a lot of small files or small objects, throughput also could be a measure of how many transactions per second or how many operations per second you can drive to storage. And the last consideration is latency. So latency is really just how long does it take round trip for you to perform a really small operation to a storage solution. With S3, when we talk about latency, often we talk about first byte latency. This is the time it takes for S3 to start giving you data, but not necessarily the end time of data being served. Latency is really important, one, because it can impact throughput and IOPS, depending on the concurrency of a workload. And the second is it also is a measure of the responsiveness of a storage solution. A lot of the workloads that we work with customers on have a component where they're large compute clusters processing large volumes of data, but at the same time, that data is also used by end users, by researchers who are working with the data, manipulating the data. And especially for a lot of these human-in-the-loop types of use cases, having your storage be fast, responsive, not feel like it takes seconds or minutes to perform an operation really matters to these end users. So when we work with customers who are looking to build or run high-performance workloads in the cloud, there's typically two patterns that we see. And in our presentation, we're going to double-click on each of these. The first is we talk to a number of customers who have existing large volumes of data that are stored predominantly in Amazon S3 on AWS, and they have a data lake that's in S3. And what they want to be able to do is to take that data and do more with it. Run more analytics against it, build models based on it. Again, but the core starting position is customers have an S3-based data lake. Quick poll out of show of hands, who here has an S3-based data lake? You're looking to do more with the data. Where does this bubble resonate? Okay, it's a pretty sizable fraction of the group here. The second use case that we often see is customers have existing workloads that they've already been running outside of AWS, most commonly on premises, and they're looking to lift and shift that application, the workload, and the data that it depends on over to the cloud. Typically, these workloads are file-based. I'll get into why that is a little bit later. But again, this is another pattern we see where customers may not have a given workload yet in AWS, but they're looking to bring it over and do so in the simplest way possible. Quick show of hands, for whom does that second bubble kind of resonate with? Okay, about 30% or so of folks. So as I mentioned, we're now going to double click into each of these, share some architectural patterns, some best practices we've seen working with customers in these spaces, starting with S3 Data Lake customers. And for that, I'll hand it back to George.
Thanks, Andrew. All right, let's talk about Amazon S3. There we go. All right, so let's start off. Why does anybody use Amazon S3? Amazon S3 is the old mainstay. It's been around for 18 years. It is your de facto cloud object storage solution that has virtually unlimited storage scalability. It dynamically scales to your workload, all without any pre-provisioning or capacity management needed on your part. And of course, you only pay for what you use right there. S3 is known for its 11 nines of durability, as well as its 3 AZ regional availability. It is particularly useful for any of your most sensitive or precious data to be stored. But why Amazon S3 specifically for data lakes? So we're specifically going to be talking about our general purpose buckets, which I have highlighted right here. Amazon S3 for data lakes is particularly great for large-scale data lakes that have varying access patterns and long-living and growing data volumes. Petabyte to petabyte, S3 standard and subsequent colder classes, such as standard and frequent access and Glacier instant retrieval, have the lowest storage costs available with increasing request costs as storage get colder. This means that if you need long-lived data set that has periods of low usage, using Amazon S3 is going to be the most efficient cost solution for your use case. Of course, a lot of customers monitor their usage of their objects and their data and move them independently between these different storage classes to try to optimize costs. Additionally, you can use S3 intelligent tiering to automatically move that data with S3 monitoring your access patterns. Now, we've talked about how and why you would use Amazon S3, but now let's talk about how you can get the most out of your Amazon S3 data lake. To get the most out of Amazon S3, you really need to be looking at taking advantage of Amazon S3's scale. First and foremost, working backwards from your workload performance requirements as well as your compute and network resources availability, you should be able to understand what sort of throughput you need for your workload. Amazon S3 general purpose buckets provide 95 megabytes per second for each connection, allowing you to effectively parallelize and scale horizontally any of your workloads to gigabits or terabits per second, whatever you need to saturate your NIC, GPU, or CPU. Now, this parallelization works best when it is well distributed. If you hotspot, you're going to have a more inconsistent experience. In order to be well distributed, you should be using multi-value answer DNS technology that provides 8 answers for each DNS, as well as a short-lived DNS cache TTL. If you're using the Amazon AWS SDK, this is already automated for you. If you're having your own client, you're going to want to set that TTL to 5 seconds or less. All right, S3 general purpose buckets, as most of you probably know, scale by prefix. It starts at 5,500 reads per second and 3,500 writes per second. As your workload increases on the prefixes that are available to you, this automatically scales up to whatever TPS or request capacity that you need for your prefix. While it's doing this scaling, customers do receive slowdown messages, and as the system scales the request capacity, that can happen over minutes right there. And when we're talking about high performance workloads, this is not as desirable. For high-performance workloads, we recommend a thoughtful prefix design. So up here, I've provided two very basic examples of prefix design to kind of talk through the scenario. In the left-hand side, you see a very basic date and platform prefix design. You can see it's kind of like for an autonomous car right there, where each prefix is kind of based on a date and a car number right there. Each one of those prefixes is going to be initialized with the 3500 and 5500 until the load gets up and it can actually scale again. Now, if we take a look at that date and platform prefix design, you'll notice that if I added a new car, say car 010, this would end up sharing the same prefix as car 01. So when you're using just while this works for many, many workloads to actually have it easily subdivided by date and platform, you can run into accidentally and unintentionally sharing prefixes. To get around that, we have the example that is on the right-hand side of the screen. In this example, we've added entropy or randomness to the beginning of the prefix to ensure that as your workloads grow, they're on independent prefixes and initialized to the TPS that you need. All right, so we've talked a lot about how using general purpose buckets is great for our varying access pattern and infrequent access data with data lakes. But what if your use case is extremely hot? What if it's not long-lived data? What if you have a short period of data that you are just going to hit really, really hard, do a training, do an activity on it, and then you're either going to checkpoint or shuffle that data off or even delete it after that? This is where S3 Express one-zone directory buckets come into play. This is for your most frequent accessed data. Amazon's S3 Express one-zone provides highly consistent single-digit millisecond first byte latency. You can bank on that. As the price and performance goes up, we've actually reduced the cost for request cost by 50%, which makes it purpose-built for those extremely high TPS loads from a financial right there. In order to get this performance, let's talk about and compare Amazon S3 directory buckets to our general purpose buckets. We talked quite a bit about prefix design earlier. In the case of Amazon S3 Express one-zone directory buckets, there is no prefix. It's no longer that flat design that you've been used to for 18 years. When you initialize a bucket in S3 Express one-zone, you instantly get hundreds of thousands of TPS right out of the go. This is a hierarchical index that allows that to happen right there. Additionally, as we keep on saying one zone at the end of Express, this means that this storage class is a single availability zone rather than a regional storage class. Why would we do that? This allows you to literally co-locate your compute cluster with your storage inside the same VPC, inside the same availability zone. You're literally getting the closest physical and logical connection to your data that you possibly can in the cloud object storage. Finally, I do want to talk about how authorization is different in Amazon S3 Express one-zone. It uses a session-based authorization model where you go, create a session, you get a token that lasts for 5 minutes. That token will either give you read-only or read-write access to the entire bucket. It's very much simplifying your security model right there and allowing you to very quickly not have to deal with any of that overhead for authorization on your actual compute workloads. If you're using the, again, and this is going to be a theme that you hear throughout this, if you're using the AWS SDK, this session creation and usage is completely automated inside of there, as well as the CRT. Okay, so now we've talked a little bit about how to use Amazon S3 general purpose buckets as well as using Amazon S3 Express One Zone directory buckets. Now I'm going to pull it all together in a real world example with ClickHouse. ClickHouse is an open source column-oriented database management system that is designed for real-time analytics. It's well known for being extremely fast and extremely efficient in its capabilities. How ClickHouse works under kind of the hood is that initially as data comes in and it's hot and it creates small immutable parts that are utilized for the analysis right there. As the data gets colder, they combine these parts into larger parts, and that is kind of the colder data as it goes through there. The advent here that ClickHouse did is they used a two-tier system using S3 Express One Zone as the first tier. As these parts were being created and the analysis was actually being run, that portion was actually ran on S3 Express One Zone, and this was their super high, most frequent data accessed right there with the lowest request costs. As the data became colder, they did the merge operations again on Express One Zone and then moved that data to general purpose buckets in S3 Standard. Ultimately, this allowed their query performance to increase by 283%, but actually lowered their total cost of ownership by 65%. All right, now I'm going to turn it over to Andrew, who's going to talk a little bit about lift and shift file storage customers.
Cool. Thanks, George. So as George mentioned, I'm going to talk a little bit about lift and shift file storage customers, some of the use cases, patterns we see here. Also, just as a quick teaser, I'm also then going to talk about some of the design patterns we see for customers who are actually using S3 data lakes along with their file solutions together. But again, I'm going to start really with the lift and shift use cases. So as I mentioned earlier, when we talk to customers who have existing high-performance workloads that they're running, predominantly these workloads are using file storage solutions to power the workloads. Why is this? Well, there are a few reasons that we've seen. The first is file systems are a familiar way to access data. Most operating systems out there, whether it's Linux, Windows, Mac OS, they present data as files and folders. And network-attached file systems similarly present data in the exact same way. Most end users and researchers know how to work with files and folders. The second is file systems are POSIX compliant. They support capabilities like locking, like strong consistency. And this becomes increasingly important if you're running workloads that span many compute instances to make sure that as your workloads are accessing and modifying data, you have a consistent point-in-time view of the same exact data across all of your instances without things like eventual consistency. The third is file is easy to share. Most of the customers we talk to have, they are used to running compute clusters where they have a /shared folder. And that folder exists on every single client that they have, and that folder maps to a file system. And so, again, the end users who are used to interacting with data are familiar with, okay, /shared is a shared system, and they may not know the details of how it works under the covers, but they're used to being able to access this shared pool of storage regardless of which instance they log into. And last, but definitely not least, is file systems are performant. Network-attached file systems have been around for decades, and over this period of time, there have been a lot of capabilities and improvements that have been made to file systems that are really focused on optimizing performance, and this is specifically throughput and latency. On AWS, for customers who are looking to bring high-performance file-based workloads over, primarily what we see customers choose is our Amazon FSx for Lustre service. Quick show of hands, how many folks here are familiar with Lustre as a term? All right, actually quite a few folks. So Lustre, it's a really powerful open source file system that, if you know nothing else about it, it's really optimized for speed. It's built for high performance, it's built for high levels of aggregate concurrent throughput. And Amazon FSx for Lustre is a service that Amazon launched about 6 years back, actually reInvent 2018, exactly 6 years back. That is an Amazon native service that is built on Lustre. Our goal with FSx for Lustre is to give customers the high performance capabilities that Lustre provides without customers needing to become experts in how do I manage a large scale storage system. So what I'm going to talk about first is we talked about throughput and latency being kind of the two predominant characteristics that customers look for when choosing a storage solution. I'm going to first talk about latency, as this is really an area where file systems and FSx for Lustre in particular really shine for high-performance workloads. So when we built the service, we intentionally built it and architected this product in a way to offer the lowest possible latencies that we could on AWS. And there's a few ways in which we did this. The first is file systems are built on SSD storage. SSDs are known to provide really low latencies, tens, hundreds of microseconds of latency, super fast. The second one, and this is a particularly challenging design decision, but one we felt was really important, is when you have a client that's mounting a file system and you're going to access your data, that network is a single round trip from one server to another. When we look at many other storage solutions that are out there, many of these solutions have networks of servers where a client reaches out to one server and then behind the scenes there's another server it needs to get routed to. Or sometimes we'll see solutions where there are load balancers or proxies that sit in between the clients where you're running your workload and the actual servers that have your data. All of these kinds of architectural patterns, there are really good reasons why they exist, but all of them do add latency because, rather than taking a direct flight, it's like needing to have a layover. And so we've purpose-built the service in a way where when you have a client and you're accessing storage, it's one network hop to get to the server that has your data and back. Lastly, Lustre itself has a number of caching capabilities that are built in, both for reads and for writes, and both on the server side and on the client side. We recently did a quick analysis to see what % of IOs on FSx for Lustre are actually served from a cache. It's the vast majority, actually, when we took a look. And this really speaks to the power of these caching capabilities. At a high level, what this really means is if you're running a workload where you're, let's say, processing the same data multiple times, there's a really good chance that the subsequent time you read the same data, it'll be served from a cache and will be much faster than even the first time that you read it. So why does this all matter? Here I have a quick graph of, we took an example autonomous driving data set, A2D2. It's a data set that Audi put together. This is comprised of millions of images, on average around 30 kilobytes in size, and compared the time that it took to just read these images in using a single process. So George mentioned earlier the latency differences between S3 standard and Express 1 zone, and that really accounts for the difference in performance you see on the two leftmost bars. All of the capabilities I just talked to you about on FSx for Lustre that are really optimized to further reduce latency to the sub-millisecond range, they account for the difference between the middle and the rightmost bar. It's about a 5x difference. Again, there's a bunch of patterns, in terms of parallelization, and there's ways to get really high performance regardless of the storage solution that you're using. But the reason I wanted to spend a moment just to highlight latency is the number one value proposition we see with latency is that having a low latency storage solution allows you to spend less time agonizing over architecting around the latency of the storage system you're using. We work with a lot of customers who have I/O patterns that are not particularly friendly for network-attached storage solutions, doing small random reads and writes. And while these may not be optimal I/O patterns when you're trying to read large volumes of data, they work when your storage system is low latency enough. And so this is how latency matters, and this is why I wanted to spend a few moments touching upon it. So the second dimension of performance is throughput and IOPS. Here, really, I have 3 recommendations I want to go through pretty quickly to share how you can optimize the throughput and IOPS when you're using FSx for Lustre. The first is, and this is probably the simplest, is you provision a level of throughput with the service. The way that it works at a high level is with FSx for Lustre, when you create a file system, you choose a level of storage capacity, and you choose a throughput tier for the file system. Now, a throughput tier determines the level of throughput that file system can support per terabyte of storage. We offer 4 different throughput tiers on FSx for Lustre, ranging from 125 megabytes per second per terabyte of storage on the low end, and scaling up to 1,000. The reason we offer a few different throughput tiers is to allow you to cost optimize for the storage and the performance that you need. But again, at a high level, recommendation number 1 is make sure when you're creating a file system, you're provisioning enough throughput based on what you expect your application is going to need. And you do this by choosing the storage capacity and the throughput tier. The second is, earlier this year, back in June, we actually launched a capability around metadata IOPS that I'll talk about in a second. But before, if I rewind the clock a bit, with FSx for Lustre, there's really two components of performance that matter. There's the throughput, which determines really how much data read or data write throughput you can drive at a given point in time. And the second is metadata performance. These are two separate performance buckets. Metadata operations are operations you perform not on the contents of files, but rather operations you perform on the file system tree itself. Things like creating a file, deleting a file, listing the contents of a directory, getting permissions. All of these are metadata operations. Most use cases on Lustre and most use cases that are high performance end up being really heavy on throughput, less so on metadata IOPS, especially when you're working with really large files or really large objects. So for the vast majority of use cases, metadata is not really a limiting factor or an area of concern. So by default, we bundle metadata in with the storage capacity you provision. By default, metadata performance isn't really something that you need to worry about thinking about. However, over time, we've been seeing customers increasingly looking to use our storage products, not just for high-performance computing, but also for home directories, end-user research workstations, more interactive workloads that are heavier in metadata performance. So for this reason, earlier in June this year, we launched a new capability that basically allows you to get up to 15 times higher metadata performance on FSx for Lustre. And as part of this feature, we also gave customers the ability to provision metadata performance independently from storage. So the high level here is if you have a use case that works a lot with metadata, again, end-user research workstations, small file type workloads are kinds of use cases where metadata performance may matter. As of June, we have a new capability that allows you to get much, much higher metadata performance on the service. We have a dashboard that we launched earlier this year as well, where you can see your % utilization of your metadata resources, and you can scale up your metadata performance as needed. So this is really just, again, it's a use case that matters mostly for kind of small file or metadata-heavy use cases, but something I wanted to share because this does matter in terms of optimizing performance for some of those workloads. Now, number 3 I want to mention, and this is actually a new capability that we launched just last week, really excited to talk about with you, is as a performance recommendation that we have is to enable a new feature that we launched on FSx for Lustre, which is enabling elastic fabric adapter support. Who here is familiar with EFA? Okay, about a third of the room. So EFA is a networking technology that Amazon launched back in 2019, about 5 years back. At a high level, it's built on a custom protocol that's not TCP-based, but it's built in a custom protocol called SRD that is designed to provide higher performance scalability and lower latencies than traditional TCP networking. One of the things that we've seen with customers is, as I've been at Amazon for about 9 years. When I started, the largest EC2 instance that we offered supported about 25 gigabits per second of network bandwidth. A few years later, that increased to 100 gigabits per second of network bandwidth. And as of last year, we launched P5 instances that have 3,200 gigabits per second of network bandwidth. And not only are these numbers increasing over time, but customers' desire to need that level of throughput for these workloads is also increasing. On FSx for Lustre, what we've seen is with traditional TCP-based networking, due to the networking layer itself, as well as TCP networking requires the use of the OS kernel to handle networking traffic. Due to a combination of these two limits, we found that if you're trying to drive high levels of throughput to a network-attached storage solution like FSx for Lustre, typically you get performance capped to about 100 gigabits per second. With EFA, what we're able to do is bypass the kernel of the operating system that's running on your EC2 instance and leverage this new SRD protocol that Amazon has developed to deliver even higher levels of performance scalability. So with EFA by itself, you can get up to 700 gigabits per second of network bandwidth from a single client. Again, Lustre is designed to scale, so if you have tens of clients, you can get orders of magnitude more performance of this in aggregate across your file system. And with EFA and some of the OS bypass capabilities we've launched, we also now support NVIDIA GPU direct storage. At a high level, this is a capability that lets you bypass your CPU on your clients to directly have the GPUs that are running on a P5 instance directly talk to the network card on your client and go out to storage. With GDS, we're able to deliver up to 1,200 gigabits per second of throughput to a single P5 instance. Again, these are all per client limits, and you can get multiples of these numbers with multiple clients. Now, in addition to these performance scaling capabilities, which we're really excited to launch because we have customers who are saying, even though 100 gigabits per second is a big number, that still may not be enough to fully saturate a GPU instance. In addition to these performance improvements, two other really cool side effects of EFA and GDS is, first, with GPU direct storage, we're seeing up to a 70% reduction in the CPU load on a client simply to drive network I/O. By taking the CPU and by taking the OS kernel out of that data path, you can free up those CPUs, and now you can do a lot more, different kind of analysis, different kind of work with those same resources. These are your CPU resources running on your clients. The second is, with SRD being a lower latency network path, we're seeing single stream latencies, single stream throughput increase by about 20%. So put differently, single stream latencies drop by about 20% simply by switching over to this SRD protocol. So as I mentioned earlier, this is a new feature we launched just last week. I'm really excited to be talking to customers this week at reInvent and seeing how they're looking to use it. But again, in terms of performance recommendations, this is number 3, enabling this really powerful capability to give you even better performance for your high-performance workloads. So with that said, I'm going to leave off on the file lift and shift section just with a quick customer anecdote. So I'm going to talk a little bit about Shell. Shell, they had an on-premises environment a few years back, GPU-based, where they were running into some bottlenecks in terms of the infrastructure resources that they had on-prem. At a high level, Shell, given that they had a file-based environment on-prem, they wanted a similar environment in AWS as well. They were looking to burst over to AWS for excess capacity. And they were able to use FSx for Lustre, as well as EC2, leverage the fact that they can now scale up and scale down their compute and storage resources, which is something they couldn't do on-prem. And ultimately, this added flexibility and the high performance storage that they get on AWS allowed them to increase their GPU utilization from 90% to about 100% in the cloud. So 10% may not seem like a lot, but for those of you who've paid for a P5 instance, you know that every percentage point matters. And again, this is really the power of having really fast storage to allow you to drive full throttle on the compute resources that you're paying for. So with that, as I teased a bit earlier, we talked about S3 data lake customers, and we talked about file lift and shift. There's another use case we commonly hear from customers, or an ask we commonly hear from customers, which is customers have existing S3 data lakes that they've built, but sometimes they want access to that data through a file system. And so I want to spend a few minutes to talk about some of the capabilities that we offer that make it easy for you to do exactly this, get file access to data that you have in S3 data lakes. So you may be wondering, well, why would I want file access to S3 data lakes? S3 is an object service. There's really 2 reasons this comes into play. The first is you may have file-based tools and applications that are really written to assume that the data they're working with is in a file system. But if your data is in an S3 data lake, having a capability that allows you to access that data as if it were in a file system becomes a really powerful capability. The second is, I just spent a few minutes talking through some of the really rich performance capabilities that file solutions have to offer. And oftentimes, putting a file system or having file access to object storage allows you to benefit from some of these file performance characteristics to get even more performance, to really accelerate your workloads relative to accessing data on S3 directly. So when we look at options to access S3 via a file interface, there's 2 key solutions that we spent a bunch of time putting together and that we see customers use. The first is a technology called Mount Point for Amazon S3. What Mount Point is it's a Fuse client that runs on your EC2 instance. And basically what it does is it exposes a file system mount so it exposes a folder on your EC2 instance. And under the covers, Mount Point communicates with an S3 bucket in your account using standard S3 APIs: get, put, list, delete. Mount Point, and so you can think of it as kind of a file translator to S3, if you will. The second solution is with FSx for Lustre, we actually offer a native integration between FSx and S3. The way that this works under the covers is when you create a file system, you can choose to link it to an S3 bucket, And what we will do is we'll basically make the data that's in your S3 bucket accessible via your file system. Under the covers, we get the listing of all the objects in your bucket, populate it in the file system. If you try to read data from your file system, you'll actually see the objects that are in your bucket as if they're files in your file system. And as you add more data to your bucket, we'll automatically import them into your file system. And as you write data to your file system, we automatically export that to your bucket. So you can think of it almost like a file system cache in a way that sits in front of your S3 bucket. At a high level, between these two types of solutions, MountPoint ends up becoming a really great solution for workloads that, that need file capabilities, but that don't necessarily need the full semantics of a file system or the full performance that a file system has to offer. So the prototypical use case for MountPoint is one where, for example, you have large objects in S3, so latency isn't as much of a factor, and you're looking primarily to just read that data, stream that data. MountPoint is something that supports, again, gets. It offers pretty high performance for access to data on S3. It's a great solution for these kinds of use cases. Because S3, for example, doesn't support the notion of renaming an object or renaming a folder, for example, or locking data. These are all features really that file systems are built to support. Any more interactive workloads or workloads that need these capabilities may not be a best fit for MountPoint. And that's where FSX for Lustre comes in. So with the FSX for Lustre architecture, your compute instances are actually interfacing with the file system. So you get full POSIX semantics, you get all the same consistency guarantees that you would if you didn't have an S3 bucket behind it. And the file system itself, we've spent a lot of time writing capabilities on the file system to make sure that as you're making changes to your bucket or to your file system, those get reconciled and those get propagated correctly to each data source. So at a high level, again, MountPoint is a simpler solution in many ways because you don't have a file system in between your clients and your bucket. FSX for Lustre gives you a higher fidelity solution in terms of really giving you a more first-class file experience if you need features, again, like locking capabilities or rename capabilities or maybe modifying existing objects. So these are two ways to get file API access to your S3 data. The other reason I mentioned why customers look to put file in front of object is sometimes for the latencies. So to give you an example, we actually did some testing on our end. We took a Kaggle data set. This is a liver data set that exists it's a public S3 data set. And we measured the time that it takes to run patient classification of this data set with a few different configurations. One of these is if you're reading directly from S3. So in this use case, we're downloading the data from S3 onto local storage, and then we're running the training workload against that local storage directly. And the second column in the middle, what we did instead is put FSX for Lustre in front of S3 data, and then loaded the data from your S3 bucket into the file system. So this example ended up being 67% faster than reading from S3, downloading from S3 directly. And this primarily comes down to, again, the lower latencies that FSX provides that we talked about earlier. As I mentioned earlier, Lustre has a bunch of caching capabilities built in, and so the difference between the second and the third column is really that. If you run the exact same workload a second time without touching anything else, we're seeing that second run is 83% faster than the first. And the difference really between that second and third column is automatic. This is the caching features that I talked about earlier. Speaking of caching, with MountPoint for S3, there are similarly caching features that are built in that allow you to optimize performance to data. So MountPoint, when you configure a MountPoint, you have the ability to choose a local cache. You can configure a local NVMe drive or an EBS volume to serve as a cache for frequently read data. And with this capability that's built into MountPoint, what it means is with subsequent accesses to data, you can get roughly up to 2.2x faster performance than if you were reading the data multiple times from S3. The other capability that we launched just this past month is the ability to actually have a shared cache on MountPoint that uses Amazon S3 Express One Zone. So unlike the first two caching options that we've had for some time now, the first two caching options are really local to a given compute instance. And so if you had multiple compute instances all accessing the same data, each of them may have their own local cache, but they couldn't benefit from each other's caches. With this new capability, you can now configure MountPoint to automatically take eligible data that you're reading from S3, store it off into an Express one zone bucket that you've created. And what that means now is other instances in your compute cluster that are reading that same data can now have that data served from Express one zone. So this is a really cool new capability that gives you a shared cache across all your compute instances, in contrast to the two existing caching solutions, which are based on local storage. So lastly, I want to share just another quick customer example. This is LG AI Research. So this is the AI research lab that's part of LG. And what they wanted to do is create a foundational model that actually mimics the human brain. And so they decided to build their own using Amazon SageMaker and FSx for Lustre. The reason I wanted to share this example is I think it's a pretty interesting use case of this customer using a bunch of our different storage solutions really based on their strengths. This customer, as you can see on the left-hand side, see if the laser works, there we go. On the left-hand side, they're storing their machine learning training data in an S3 bucket. For both the performance and to get a file system interface, they've created a Lustre file system that's linked to this bucket, and they're accessing this Lustre file system from their SageMaker training instances. And then when they're done with their workload, the model artifacts they're storing back in S3, which they can then use for further inferencing. So here, this customer is using Amazon S3 for longer-term storage of both their training inputs as well as their model outputs. And then they're leveraging FSx for Lustre really for the highest performance data they have to accelerate their training runtimes and get the best performance for those instances that they're running. So with that said, that concludes the presentation that we had. I wanted to pop this slide up real quick. One of the benefits of a Monday session is there's a whole lot of sessions remaining for the rest of the week. So I wanted to share some example sessions of related topics that are really focused, again, on storage, optimizing storage for performance. Many of these are more chalk talk, more informal types of sessions that give you an opportunity to really get your hands dirty with some of our experts to figure out how do we, what are the right ways to put together storage and compute solutions. So with that said, I wanted to thank you all for attending. I know it's post-lunch, so appreciate you all making it out. If you haven't already, please just do complete the survey. I think you should be getting a notification in the app. With that said, George and I are going to be sticking around to answer any questions that folks may have. So if you do, feel free to raise your hands. Happy to talk through, and we can also meet in the hallway afterwards for any follow-ups. Yes?